Alright, let's get started. Today, we're diving into something really interesting, how gravity can be formulated as a gauge theory. This is a perspective that bridges ideas from general relativity and gauge field theories, and it turns out to be really powerful when thinking about quantum gravity. This introductory talk is meant to set the stage for a later, more rigorous presentation. We'll start with some fundamentals, build up the mathematical framework, and then explore how gravity naturally fits into a gauge theoretic description. Let's go! So first, let's quickly talk about gauge theories. These are the backbone of modern theoretical physics, describing fundamental forces like electromagnetism and the weak and strong nuclear interactions. At their core, gauge theories are all about symmetries, specifically local symmetries, and how they lead to conserved quantities, thanks to Noether's theorem. Now, you might be wondering, what does this have to do with gravity? Well, just like electromagnetism can be described using a gauge field, the vector potential mu, gravity can also be recast in a similar language. Instead of the metric formulation that we're used to from general relativity, we'll see how gravity can be rewritten using gauge fields. That's our goal today. Before we go into the heavy math, let's look at something fun, the falling cat problem. You've probably seen videos of cats flipping in midair to land on their feet, even when dropped upside down. The key here is that the cat isn't pushing against anything external, it's purely an internal reconfiguration. Now, believe it or not, this is actually a great analogy for gauge transformations. The cat's motion is confined to a shape space, where the only relevant degrees of freedom are internal. Similarly, in gauge theories, physical states can transform internally while preserving certain constraints, leading to conserved quantities. This idea, how internal symmetries relate to physical behavior, will be central to how we view gravity as a gauge theory. Now, let's get into some math, specifically differential forms. If you've worked with differential forms before, you know they're incredibly useful in field theory because they make gauge invariance manifest. We use things like wedge products to define volume elements and field strengths in a coordinate-free way. One key result here is Stokes' theorem, which connects local and global properties of a field. This plays a crucial role in electromagnetism and gravity. Also, the idea of gauge invariance naturally emerges when we express field strengths in terms of exterior derivatives. Ushtekar's variables, which we'll talk more about later, also rely on differential forms, specifically densitized triads, which provide a different way to describe the gravitational field. Alright, now let's get to the main point. How do we rewrite gravity as a gauge theory? First, instead of using the metric tensor g mu nu, we use tetrads, or vierbanes, which are a set of 4 basis vectors at every point in spacetime. These transform under local Lorentz transformations, much like gauge fields transform under internal symmetries in other gauge theories. Then, we introduce a gauge connection, Ushtekar's connection, which plays a role analogous to the vector potential in electromagnetism. In this framework, gravity looks like an SU-2 gauge theory, which is strikingly similar to how we describe other fundamental interactions. Now, if we want to apply this gauge theoretic approach to gravity in a Hamiltonian framework, we need the Arnowit-Dieser-Meissner, or ADM formalism. This splits spacetime into spatial slices plus time evolution, making it useful for quantization. The real breakthrough came when Ushtekar introduced new variables, recasting general relativity in terms of an SU-2 gauge theory. Later, Barbero refined this approach, which ultimately led to loop quantum gravity. So why does this matter? Well, if gravity is really a gauge theory, then we can try to quantize it using the same tools we use for other gauge theories, potentially solving one of the biggest problems in theoretical physics. So, to wrap up, we've seen how gauge theories are fundamental in physics, how gravity can be formulated as a gauge theory using tetrads and Ushtekar's connection, and how this leads us toward quantum gravity. There are still open questions. How does this approach connect to the standard model? What about coupling to matter? And, of course, does this really get us closer to a quantum theory of gravity? That's where future research comes in. And with that, questions?